Swayamprabha. Digital India. Educated India.
Welcome you all again to this course on Foundations of Computational Fluid Dynamics. We are on to module 2 of the first week. Last class we basically did, we'll put out the syllabus for the course and then outcome what you obtain from this course, some of the mathematical operations, then definition of velocity field, vorticity, viscosity, definition of fluid based on viscosity, and we still have to do review of equations, and there are other topics like non-dimensionalization, vorticity stream function and so on. Whenever a fluid is moving, you have to characterize them, visualize them. So this is given by flow visualization, and there are 4 such characteristic lines defined for flow description. They are timeline, path line, streak line and streamline. So we will see the definition of them, and later when we take example we will see that how these are used to define a flow. So timeline are the lines or curves formed by number of fluid particle marked at particular instant of time. This is very important. So it is unsteady flow, it changes with the time, and you are looking at one particular instant how different fluid particles at that instant behave, and if you are able to connect all the particle at that instant, then similarly you proceed with the time, you are able to get timeline for that flow. So they get displaced as the particles proceed further in the flow. Path line is another definition. This is a contour of path followed by fluid, moving fluid particles. They are traced by individual fluid particles, and in experiment also in CFD you can inject a dye, then it traverses, then if you connect all the contour then you get path line. So path lines are characteristics Lagrangian description of the fluid motion such that the coordinates of the fluid particles can be expressed in terms of time as well as initial coordinates. There are other 2 definitions, streak line and streamline. So streak lines are the locus of all fluid particles which passes a particular point, and after some instant whatever particle that is crossed at that particular point and you connect all of them, then you get a streak line. So in experiment if a dye is injected, then it would continuously move only along the streak line. Streamlines, so this is a standard definition which all of you know, a family of curves which are tangent to the direction of the flow at every point at a given instant. So if you draw a tangent to a streamline, then you get velocity component, velocity vector at that particular instant. Your streamlines show the direction in which the fluid element would tend to move at any point of the flow field. We know a flow can be steady or unsteady. So, in steady problem, all these 4 description, path line, timeline, streamline and streak line, they all will be same. They will be different for unsteady flow, and this is to be noted very carefully. Now, next important topic, reviewing of basic equations. We will not do detailed derivation, we will only touch few steps and explain importance of terms. Detailed derivation is available in any standard undergraduate fluid mechanics textbook. In general, there are 3 basic equations. One is a conservation of mass, which is also known as continuity equation, conservation of momentum, and then conservation of energy. Primarily, conservation of mass and conservation of momentum are necessary for any fluid mechanics problem, and conservation of energy is used whenever you are interested in compressible flows or to do with the heat transfer problem. These are only primary equations. You also need to have additional equations depending on the problem. For example, ideal gas equation is used in compressible flows, and if you are interested to find out concentration distribution, for example pollutant dispersal problem, then you are interested to find out particular concentration, then you solve additional species transport equation. Governing equations can be expressed in 2 different forms. One is a differential form and integral form. Similarly, we already seen last class different coordinate system, Cartesian coordinate system, cylindrical coordinate system and spherical coordinate system. So, one is able to convert or derive governing equations in any coordinate system and convert from one coordinate system to other coordinate system. So, before going to the derivation, one important concept that we have to learn in fluid mechanics is what is known as a system and control volume. System is basically related to a fixed identifiable mass. So, with the time the boundary may change, but the mass remains. So, then the boundary which contains that mass may change, but the quantity of mass that remains same. So, across the boundary you can have a work or energy transfer. The usual example given is piston and cylinder assembly. Certain quantity of gas is inside the cylinder and piston moves front and back, the mass that is remain is the same, and you have an energy transfer happening across the boundary and piston moves back and forth. Now, though it looks simple, for a problem where there is a continuous change of the boundary, it is difficult to apply idea of system or concept of system and get a solution. So, there is an alternate what is known as a control volume, where you do not really focus on a fixed quantity of mass, only the boundary, focus on fixed window and then observe what is happening to that window. So, we can have a mass transfer also in addition to momentum as well as energy transfer crossing the boundary. Control volume can change shape or move, it need not be fixed in a flow, it can also move. For example, you want to find out flow past an aircraft or flow moving over a 4-wheeler, and you define control volume around the aircraft or four wheeler, as the aircraft moves or as the four wheeler moves, the control volume also moves. Similarly, if you take a balloon, then the balloon, as you are deflating, it changes its shape. So, the boundary which is defined here as a control volume, it can change shape. This is helpful. For example, you have an elastic material and you want to find out fluid structure interaction problem later, then there is a boundary, it is not fixed, it undergoes changes as a function of time. Control volume study is very helpful. The boundary which is enclosing the control volume is called control surface. So, there is a schematic available. So, here this red boundary is a control surface and the fluid crosses through the control volume, and you find out what is happening to the control volume because of the flow that is happening through this control volume. So, for example, you want to find out in the case of aircraft what is the lift generated, what is the drag force exerted on the aircraft, then you find out net and then get a drag estimate. So, as I mentioned before, one can get all the governing equations either in integral form or in differential form. We will see some of them in integral form, then later we will move to differential form. So, to get an integral form, we can relate the system and control volume derivatives for any general extensive property n. Then one can get all basic laws by instantaneously identifying system and that coincides with the control volume. This is theory what is known as the Reynolds transport theorem. Right now we are not going to the details of the derivation. In mathematical form it is expressed and given here. The extensive property n is related to intensive property eta, and it is related here as n equal to integral over mass, which is for actually system. Eta into dm is related to volume, which is for the control volume, and eta rho into dv. Now, you can see by substituting different values for eta, you get different governing equations. For example, if you say eta equal to 1, so if you substitute eta equal to 1 here, and then the resulting quantity corresponding extensive property is actually the mass. So, if you put eta equal to 1, it is integral rho into dv. You know rho is the density kg per meter cube and dv is meter cube, product of them will give you mass. So, that n is actually mass and that will give you consideration of mass equation in integral form. Similarly, if you define eta intensive property as V, then if you substitute here V, so V into rho into dV, you know mass into velocity will give you the linear momentum, and similarly on the left hand side extensive property n will give you the linear momentum. So, you can substitute different value for eta and they are given here. Next one is for angular momentum, then total energy and total entropy. So, one can obtain from this general relationship between extensive property and intensive property to this integral relationship, one can obtain basic laws in integral form. As I mentioned before, this is what is known as the Reynolds transport theorem. Now, we will see how to get expression in detail for conservation of mass. We know this equation is stated as rate of increase of mass within the fixed volume must be equal to net flux crossing the boundary. So, if you consider a control volume, mass that is inside the control volume is rho into dV. V is a volume that is given here V, and then if you define at any point dA is a normal vector and V is a velocity vector and A is the area of the boundary volume. Okay. So, if you express conservation of mass in integral form, so dou by dou T of rho into dV over volume V is equal to rho V dot dA, because area is also a vector, velocity is also a vector, you do the dot product, you get a flux crossing, and here it is dA is continuously changing for this illustration figure that is given. So, you find out net flux crossing the boundary. It may be coming in some place, it may be entering the volume, in some place it may be going outside that volume, and you sum them up you get net. That is why we do integral. The integral corresponds to summing and you get that sum, and that is related to rate of increase of mass within that control volume. Now, the differential form of the equation is d rho dou rho by dou T plus del dot rho V equal to 0. We have already seen this different operators, right. So, V is a velocity vector, and in Cartesian coordinate system you have u, v, w as a component defined of the velocity. So, we already seen, we will now see in detail. So, let us take a volume 3 dimensional representation here, fluid element, and with the elemental length defined in each direction. For example, dx is the length of the element in x direction, dy is the length of the element in y direction, similarly dz is the length of the element in z direction. So, Reynolds transport theorem we have already seen. So, if you substitute eta equal to 1, then you get n on the left hand side to be mass. So, that equation is put here again, and volume is taken inside. So, dou by dou T of control volume rho into dV will give you the mass, and this will give you the flux crossing the control surface, and you find out flux crossing at each control surface and you sum them up. So, in this case if you consider this is a rectangular volume element and you define, for example, this is one face and this is another face, front face, back face and so on. So, there are 6 faces here, top and bottom. So, one has to get explanation of this term on all the control surface. So, the first term is dou rho by dou T into dx into dy into dz. Dx, dy, dz corresponds to volume, and dou rho by dou T is multiplying the dx, dy, dz will give you rate of change of the mass. Now, if you consider the next term, second term in this equation. So, as I mentioned, if you consider rho, if you consider center of this volume x by z, then from the center if you go to the left in x direction it becomes dx by 2. Similarly, from the center in the x direction if you go to the right, that elemental length is dx by 2 positive, right. Similarly, you can go from the center, come front and go to the back, that will be dz half. Similarly, top and bottom, that will be dy by 2 half in either direction. So, this term which is accounting mass flux through control surface, and you find out the term for each of this phase. So, x minus dx by 2 will be the left phase, x plus dx by 2 will be the right phase. Similarly, y minus dy by 2 will be the bottom phase, and y dy by 2 will be the top phase. Similarly, from the front and back. So, there are 6 terms for this cuboidal element that you have considered, and if you write for example only for the left phase, mass flux through the left phase, rho x y z t, that is defined here, assume that is a density available at center of the element, and you go left hand side, and this will give you the flux that is crossing, and this will give the flux that is leaving. So, you can say mass flux through the left phase of CV and mass flux through the right phase of CV. So, you get term defined like this for each phase and put them in this equation, and finally in all you have dy, dz and dx term, which is actually the volume. So, if you do that arithmetic, substitute for all phases and sum them up, if you do that arithmetic and divide by volume dx, dy, dz, that term appearing in all the 3 terms of the spatial as well as on temporal, if you divide by the volume, then you get dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. And you also know how to convert or write in other form, is dou rho by dou t plus del dot rho into v equal to 0. Okay. Now, what we have done is a generic, and it is not particular to any situation. Generic equation gets reduced or simplified for different situation. For example, in steady flow we know the properties do not change with the time. So, any term with the time derivative is there, it will go to 0. In this case it is dou rho by dou t. So, that first term dou rho by dou t goes to 0, and mass conservation equation gets reduced with only a spatial derivative term that is given here, and in terms of vector del dot rho v equal to 0. Another simplification, if it is incompressible flow, we know density is a constant. So, any derivative, any spatial derivative of density will not be there, and that term also is removed, and you get only the velocity component. So, dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0, and in terms of vector it is del dot v equal to 0. So, the next equation we said we will do 3 equation: conservation of mass, conservation of momentum and conservation of energy. The second important equation is conservation of momentum, which is based on Newton's second law of motion, F is equal to ma. Like we did for conservation of mass, here also we need to consider elemental volume, find out net force acting on the control volume, and then net momentum flux crossing the control volume. You account for both of them, then you get finally conservation of momentum equation. So, it is stated as net force on the control volume equals rate of change of momentum within the control volume and net flux crossing the control volume. So, in vector form, here again we are not doing the detailed derivation that is there in any standard fluid mechanics textbook or any other open source material or other NPTEL course. So, in vector form the consideration of momentum is given here, rho into dou v by dou t plus v dot del into v, which is on the left hand side, equals pressure gradient, viscous force and any other force. Now v is a velocity field and this del squared v, which accounts for shear force, is a Laplacian operator and given here as del squared by del x squared plus del squared by del y squared plus del squared by del z squared, and mu we know is the dynamic viscosity of the fluid. So, if you divide equation by rho, then you get mu by rho nu 1 upon rho into del p and only the external force. So, if a problem you are applying to a problem on say involving the magnetic field, then this external force Fe represent additional magnetic force. Similarly, a problem involving in gravity, then you have a gravity force appearing as additional source term. So, this is given as a source term, and for different problem we will have a different definition of the source term or external force. So, if you look at this equation, on the left hand side you have one component for time derivative and this del 3 component as a spatial derivative, and this is a derivative of time, you know, that gives acceleration. Similarly, this term also supposed to give acceleration. We will get the definition clarity the next slide. So, the left hand side is acceleration and the right hand side pressure is a force, viscosity also shear force or any other force. Okay. So, that is why I said Newton's second law, F is equal to m into a, is actually is a first principle based on which the conservation of momentum is derived, and you are able to see here the same acceleration terms and force term on the other side. We have already seen in the first class different review. We have seen total derivative, which is d by dt, capital D by dt equal to time derivative dou by dou t plus v dot del. So, if you substitute the definition of material derivative or substantial derivative, total derivative in the momentum equation, then it is rewritten as given here. So, d by dt of v on the left hand side, the right hand side is the same, pressure force, viscous force and any other force. It is convenient to write in vector form, sometime it is easy to write equation in scalar form. So, we will also get to see how to write momentum equation in scalar form. So, for example, we know 3 dimensional representation x momentum equation, a detailed expression of the same momentum equation for x momentum equation. We know the velocity component along the x is u. So, dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z, and this corresponds to expansion of this material derivative d by dt of v on the left hand side, and pressure term dou p by dou x is appearing here for pressure, viscous force is appearing here, and then the external force is considered as gravity force, and we take a component you get rho into gx. So, where gx is acceleration due to gravity, which is considered here as external force. One can also obtain similarly by substituting for v vector in terms of velocity component for y as v and w for z, you get momentum equation the corresponding direction, y momentum equation and z momentum equation. So, if you do that, you are able to write a complete momentum equation, and you are able to see here corresponding v momentum equation or y momentum equation, and third direction w momentum equation or z momentum equation. Okay. Now, you see advantage of writing in vector form, writing in scalar form, and in vector form these three equations with so many terms are written in elegantly in simple one equation with only two terms, whereas in scalar form you are able to write in detail and one can actually locate what component responsible for what. So, while writing a code also you write in detail form, then write the code, it is easier to decode later. And this set of equation, that is all the three momentum equations with the full components written, all the terms written, is generally called Navier-Stokes equations. Navier and Stokes are two scientists who independently developed these equations, and as a credit to them these equations are named as Navier-Stokes equations. And you can again understand in this equation, if you take left hand side all the time derivatives which is given as dou u by dou t, dou v by dou t and dou w by dou t, they are all called local acceleration, and u into dou u by dou x, v into dou u by dou y plus w into dou u by dou z. So, those three terms in x momentum equation, similarly three terms in y momentum equation, three terms in w momentum equation, they are called convective acceleration, and you put them together all the four terms will give you a total acceleration. So, that is what is explained. Left hand side first term is a local acceleration, that is this term, and remaining three terms are called convective acceleration. Put together it is called total acceleration. Now, if you look at this particularly convective acceleration in closely, we see here u is a velocity field which is a function, main quantity in the x momentum equation, and dou u by dou x is the derivative of the same velocity, right. In other words, also v into dou u by dou y, v is a velocity field in y component and this is a velocity derivative. So, a function multiplying the derivative of the same function is result in what is known as a nonlinear in nature. So, such nonlinear nature of this convective acceleration actually attracts special attention, because the behavior of how to solve or how to represent u multiplying dou u by dou x in discretization is important, and we are going to focus special attention on this convective term because of its nonlinearity. The behavior and the treatment of this convective term can change the solution, results in some unstable also accuracy to some extent. So, we are going to see in detail treatment of this nonlinear convection term later. So, in this class we did important topic, flow description, consideration of mass equation, consideration of momentum equation, detail in differential form, and writing the momentum equation in vector form and scalar form, and importance of nonlinear convection term and why one should focus on convection term discretization, and how to represent different external force for different problem. So, next class we are going to see little more detail on this momentum equation and go on to the next equation, consideration of energy equation. Thank you.